here from University of Wrocławski about model completeness of algebraic groups. Thank you.
Thank you. Is this working properly? Okay. So first, of course, thanks for the invitation. It's always nice to be in Toronto. And somebody asked me at party how often I go to North America these days. I noticed for the last 20 years, I go only to Toronto, with one exception. I think I was 5 times in this period, and once at Berkeley somehow. So yeah, I really like both the city and the Peace Institute. And I show it by my actions too, yes. Okay. So I don't have this great skill and wisdom of Anand to say important things in the right way, but I think I should say something that I'm talking in place of Moshe, yes, who couldn't come here from Israel, Beersheba, for obvious reasons. Yeah, and now I don't know what to say more, but maybe just general thought that the current political situation in a way affects us all, which is kind of maybe obvious anyway. And actually his talk, I was looking forward to his talk, especially after your talk in Istanbul, and his talk would be fitting very nicely to the theme of this conference, so both model theory and algebraic dynamics. And my talk will not fit so much, so. But still I will try to be motivating and to motivate and introduce some notions for non-model theorists. So for example, what is model completeness? Okay, so the introductory part starts. Okay, so I ask this question to myself and I immediately answer in a vague way. So what is which I'll abbreviate by MC during this talk. Okay, so the answer is vague answer. It's a worse version of quantifier elimination. So first, and this will be really only for the introduction, what is quantifier elimination? So as model completeness, it has 2 kinds of description. One says that any definable set can be defined without quantifiers. No matter how complicated formula you have with million quantifiers, you look at the set it defines in your structure, which should have quantifier elimination, or modulo theory, which should have quantifier elimination, then you can find formula without any quantifiers, so like equation and non-equations defining the same set. And equivalently, which actually some equivalent condition, which I very recently started to like, that any isomorphism between substructures extends to an automorphism, but possibly of elementary extension. Okay, and just checking some facts for this talk, I noticed that for finite structures, it's totally non-obvious which ones have finite, which have quantifier elimination, and which ones have not. So just for fun, I will talk about this. It's not difficult to see that this is enough for finite structures. You don't need, well, elementary extension would not be much different. Enough. Okay, some examples. So basically, in this talk, there will be only groups and fields. So mostly that's why it doesn't fit. There are no extra operators. So this is the main reason it does not fit so well to the team. Okay, so for fields, we have full answer. Then K has quantifier elimination. If and only if it is algebraically closed or finite. Yeah, 5-second thought, if you have a finite field, then any isomorphism between finite subfields extends. Yeah, okay, and historically, this was by Kowalski. This was done by McIntyre.
By the way,
Okay.
can I say something?
Sure.
When you say you allow parameters.
Of course, if you allow parameter, I don't.
You don't allow parameters.
No. If I allow, then everything becomes, of course, definable without quantifiers. Yes, but I mean, it is quantifier elimination in the original language. So without extra quantifiers, yes. Parameters. Okay, so full answer. Okay. And for groups, actually, then I was thinking, what is known for quantifier elimination? Not good?
I think the paper is McKenna and McIntyre. There's an old paper.
I think it's a paper by McIntyre himself, 1973, Fundamenta Mathematica. Okay, then I noticed I have no idea about some general results of quantifier elimination for groups. I started to search, and there is a paper. There is a paper of Cherlin and Felgner, which is in the volume of Logic Colloquium 1980. Then I started to Google. It turned out this Logic Colloquium never happened. It was cancelled apparently in last moment in Prague. Did you try to go maybe? No.
It's supposed to be in Prague.
Yeah, that's what I read in the on internet. Huh? They said due to unforeseen, they cancelled it so late that it couldn't be replaced, and that's what I just read. So anyway, but the result is in this volume. It has many things, but it includes so like classification of abelian groups, eliminating quantifiers. Okay. Because that's true. So. Then A has quantifier elimination if and only if A is divisible or has finite exponent and for each prime, the P primary part is isomorphic to a direct product of some copies. Maybe like that. of some copies of the same cyclic group. That's the result. I think I didn't know there are non-commutative. Okay, there were non-commutative groups with quantifier elimination, like such one. Yeah, the group acts by inversion, so it's non-commutative, and also has quantifier elimination. And maybe the funniest one, maybe these things are funny and interesting only for me, but if G is finite simple, non-commutative, then G has 2E. And only if in there are just two cases, PSL to 5 and PSL to 7. They used classification. I don't know, I would not expect such a thing. Okay, I guess, who knows? Analyzing this property, one can get some conclusions, but it was very surprising for me. Okay, and just to say something related to this conference, of course, the CF0 which was used a lot in this meeting, the differentially closed fields of characteristic 0, the quantifier elimination in their natural language. Okay, that's all about quantifier elimination of quantifiers. Now the main topic, what is model complete? So again, it has parallel to descriptions, but it's weaker. So either any definable set can be defined by existential formula. So by formula of the form exist y, xy, when this one has no quantifiers. Equivalently universal one by applying negations, or, I don't know, in more categorical terms, any monomorphism between models is elementary. So preserves the truth of sentences with parameters from the domain. So obviously here, by contrast, any finite structure is immediately is model complete. One-to-one map is necessarily bijective on finite set. And now situation is much more complicated.
Monomorphism between embedding.
Yeah. Okay, it's a different function. Embedding. Okay.
Why should
Embedding. Okay. There are no relations in my language, but let's say in embedding.
the thing about finite structure, finite structure not theory is not image theory.
You want proof of this?
When you say a finite structure, you mean its theory is model complete? What do you mean?
Yes. Yes. But you can also.
You could take the theory, you could look at the finite structures. It's definitely.
Okay, any finite structure is model complete by definition, which I didn't say indeed. If its theory is model complete by definition. So model of a structure is an elementary equivalent structure. Okay, so examples. So now situation for fields is quite unclear. So besides algebraically closed, real closed, radically closed, the new class very nice and giving actually lots of counterexamples, curve excluding fields. Are model complete. And I think I will not talk much about this, but this kind of fields give counterexamples to some conjectures how model complete fields should look in general. So there are examples, give examples of model complete which are not bounded and not large, for example. So I'm not sure if there is any conjectural, even conjectural description of model complete fields. They are a bit more mysterious than quantifier eliminable fields. And regarding groups, okay. I was giving similar talk in Beijing, and I challenged the audience to say anybody knows a non-abelian model complete group. So now, of course, after I learned there is like this one, then Nick said, Nick rams the extra special ones. Okay, but they are very nilpotent. So actually our work here, which I didn't get to yet, will give many new examples of groups which are model complete. Okay, but so for example, groups. I forgot to write, I was supposed to write it earlier. I think it's also not so easy to produce examples of fields which are not model complete. The ones I have in mind. Imperfect. But after you name constants, probably there will be. That's true. That's so wide that it cannot eliminate quantifiers on any level by some other arguments. But besides that, I don't know of any general technique showing that
Any function field.
any function the same. Okay. Probably a number field, yes. So some of those, I guess, the very conjecture is that model complete are those which are tame, maybe after you name constants, because this is maybe tame, but without naming constants, it's not model complete. So our situation is not very clear. And ACFA and does not have that's so important here. So which may be, okay, I'm not sure if it's true statement, a reason that difference algebra is more complicated than differential one. Do you agree? Okay. So introduction is almost over. So we look. So I will say who are we soon. Look at some, well, natural functors from fields groups. Actually, these functors are definable groups. You have a formula, and for any field, it defines your group. In most of the cases, it will be just algebraic group, but not only. And ask whether they preserve model completeness. So it should be true. What I mean, I take this functor, some functor, model complete field. I'm asking, is application of this functor a model complete group?
So again, for the group, you mean just for the pure.
Just pure language, pure.
Language.
Everything pure. Field pure, group pure, everything pure. Yes. Okay, so usually, so mostly algebraic groups. I mean these functors. So first example, the multiplicative group does not reserve completeness because multiplicative group of QP is not model complete. Can I just say, I will say argument in words. Okay, so what's the easiest way to show a structure is not model complete? You find the monomorphism from the structure to itself such that image is not elementary substructure. Here it is taking fifth powers. It's not onto, it's one-to-one here where this is used. And clearly, since it's not onto, there are some pith roots. There are some elements in the image which will have pith root in QP star, but not in the image. So that's it. Like that is not model complete. There is the non-divisibility. Non-divisibility implies, yes, actually it's directly follows from this because it's not divisible. And the other thing. And has infinite exponent. Okay, so multiplicative group, which is actually quite, for some model theoretical properties, it's not a nice group. But still we will get many new model complete groups. Okay, so second part, joint work with Hoffman, Daniel, Mink, and Vince. So there is a bit of story, first three of them. They had worked on model completeness for SL2, let's say RC. Okay. So I heard talk of Daniel about this at Antalya Algebra Days 22, which was also sadly the last one, it seems, in Shirinja 2 years ago. Okay, listening to his talk, I noticed it's very much related with classical Borel-Titz theorem, and actually immediately follows from that. So hey, this has a quite a complicated statement. First, I will state it just for SLN, and then I will be giving more and more general forms.
The model theorist called Borel-Titz.
Huh?
Is it what the model theorist called Borel-Titz?
You tell me.
No, I'm asking you.
Well, I think it is what Poisson calls Borel-Titz in his book. Most of model theorists were not aware. Statistically, model theorists don't know this theorem, at least the one I was talking to, but maybe the, anyway, probably yes. I will state it. So we have two infinite fields. And we have, okay, so it basically describes, so it's a strong rigidity statement about abstract homomorphism between rational points. Monomorphism. Then it has relatively simple description. So it comes from automorphism of this and field homomorphism. In particular, the fields automatically need to have the same characteristic, which is something. So then there is field homomorphism. And in this version, there is an algebraic automorphism. The notation, so K is not algebraically closed, and the automorphism is defined over K. So I would say proper notation is that. It's not about K points, it's about algebraic group defined over K, or group scheme. Okay, such that, which one is first?
L is K.
Sorry?
L is K, you switched.
I switched, sorry. I'm trying to avoid the language for L, but sometimes I cannot. Such that the composition of two obvious things, which can have different notation. Let me put it like this. So diagram, we have this any abstract group homomorphism M. Okay, now a field, yes, a field homomorphism, you can just apply to the entries of the matrix, you get group homomorphism. Just use it as a functor. Okay. Sorry, it's general. What? SLM? I think it's SLM. You stopped me. I'm trying to answer your question, so I cannot say of M.
SL2
SLN. Okay, sorry. I mean that phi acts on from field to field, so I apply it to every entry on the matrix. So it's like imaged by the SL2 functor of the. One can choose different notation. And here, a map coming from this algebraic automorphism. So this is okay. So very simple description and immediate corollary. Immediate corollary that if K.
by algebraic automorphism.
Huh?
What do you mean by algebraic automorphism?
Okay, I guess in model theoretic terms, you can say it's an automorphism of SLN K-alg, which is algebraic, definable, and defined over K. Okay, for non-perfect fields defined in the algebraic sense, for perfect the same. Or we look at how algebra as you prefer. By polynomials. Yes, of course, this was totally abstract, and this is very definable, and this is just it. So it's a really strong rigidity statement. Sorry. Okay. This model complete, and this as well. Good. There is one trick. There is one trick, which actually Will Johnson told us. So first Martin Ziegler and then Will Johnson, but anyway. So take two elementary equivalent groups. And a monomorphism. Okay, now you have to believe me. So using special resplendent models, Robinson joint consistency. Yeah, all of these classical things were very new to me. we can actually assume without loss that you can check such things on, let's say, special models. And in this case, those special ones are isomorphic to SLN of something. So you can assume that there are fields elementary equivalent to M, and your groups are just SLN. And then just, okay, and then we can apply Borel-Tits. So now, Borel-Tits, this F alpha appropriate composition. This is elementary being automorphism. And this is elementary since the theory of K is elementary. So phi is elementary, and if you apply to phi anything definable, it remains elementary. That's it.
Say, Mark, it doesn't work.
Second?
It doesn't work for Q's.
For what?
Q quantify elimination.
No, doesn't work for no. And those, yes, and those groups do not have quantifier for reasons, yeah, for the reasons that they don't. Huh. Yeah, but now this was like a baby, very particular form of Borel-Tits. So I will tell you the first generalization and then the second. I mean, the generalization of this statement, which is still a weak form of Borel-Tits, I will write very soon. Okay, so I will just say you can replace SLN with any split, simple, simply connected, as in your talk, or adjoint algebraic group. I guess split, I will only use consequences of it. I think it means that if you, everything is over K, you look at the maximal torus, and it should be split. All maximal torus should be split, meaning isomorphic over K to power of multiplicative group. I think, but I didn't check. I use it kind of black boxly, so I don't care. But I think it means that. Maybe not. Okay, this simply connected means you don't have proper like extensions or covers. In algebraic world. Yeah, so SLN is simply connected, which is slightly confusing if people are used to SLN-R, SL2R, universal cover is important. So, topologically, simply connected can be interpreted over C that just C points are simply connected with the usual topology. So SLN is algebraically simply connected. Adjoint is like opposite. There are no quotients, there are no finite. There are no, not finite. Okay, basically center is trivial. Center is trivial. Like PGL. On the top SLM, on the bottom PGLM, in between as many quotients as numbers, as divisors of n. Okay, so you have tips for that. So immediately MC. Okay, so immediately such and such as here, algebraic groups preserve model completeness. That's the same argument. And then, but that's not all, then there is actual, like full, still, okay, still it is more general. Full one, we have to first, I think we need two simple split. There's a weaker assumption than split and weaker conclusion, but let's stay with split. And then we assume that either domain is simply connected or range is adjoint. Also important, the range or the domain actually doesn't have to be the whole thing. It can be anything in between commutator group and the group. So we have some this is for me commutator group. We have such a W. In our, I think we use it in this generality. And finally, we have this monomorphism. Actually, not even monomorphism. Yeah, there are some cases. E to GM with Zariski dense image. Then you get the same conclusion, but this is only isogeny. In this adjoint semi-simple case, there are no isogenies, there are isomorphisms. So I could state it like this. But C so much weaker assumptions, but also a bit weaker conclusion. And using this with lots of work, we can prove the following. Theorem. Here's our for people theorem. SMC G semi-simple split any. Then both GK and its commutator are model complete. This goes beyond algebraic groups, e.g. ESLN K commutator. So it may go a bit against the previous talk, but PSLN is not an algebraic group. This functor is not representable by algebraic group. It happened to coincide on algebraic closed fields. But in general, it's not an algebraic group. I would call it Chevalier group. Yeah, and actually treating this algebraic group over non-algebraic closed fields often causes problems. Okay, so we also cover this case, these groups, which are not algebraic. And those are really simple, yes. So the rational points to be simple, you have to go to the adjoint one and then take commutator. Normally the rational points are not simple, yes, like SLN or even PGLN. Only commutator is simple. S abstract group. Yeah. Nobody asked me what is simple algebraic group, but it's like almost simple. Questions? So that's, I think, almost the end of part 2. Huh?
What about the function SO3?
SO3.
So the algebraic closed field is the same as SO2.
I think no. I think it is here.
It's not split.
Depends what you mean by SO. There is some algebraic SO.
The SO3, like SO3R, for example. SO3 and SO2, I think are the same.
So what is SO3?
Special orthogonal.
What is SO3C?
SO2. But so it's a form of SO.
But you have to choose the form. You just choose the form, which maybe. So which form do you choose?
No, it's a form which means SO3 are isomorphic over an algebraic closed field, but not necessarily the SO3R and SO3R is compact.
But if you apply SO3 to any field, how do you define it? Then you have to choose the type of the form, and for some of them it applies, for some of them maybe not. I would have to check how it applies to SO3R. I guess it applies, I will have to check. Okay. Definitely, like SOs are on this list, but they have different meanings in general. Okay. But I don't remember the meanings. Okay. So still, I will not give any proof, which took us almost 2 years, but main difficulties in the proof exactly what you mentioned, that semi-simple algebraic group is only almost product of simple. But it is actual product on simply connected or adjoint level, which helps. Second, which is maybe even more annoying, if you have epimorphism. Thank you. Second, that taking rational points does not preserve epimorphisms. You may have epimorphism of algebraic groups, does not imply morphism on rational points. So I have two these problems together. However, it is epimorphism if K is AFC. So somehow if these two problems one has to deal and do many things, and finally it works. So one could ask what is the prediction for after removing the split.
The first thing that
the non-invocation even when K is MC.
Oh, yes, yes. Yes, for reals, I'm pretty sure. No. Yeah, basically, yes, yes. The image actually, you have epimorphism from SLN or SL2 to PGL2, but the image over R is not the whole PGL, it's PSL, which has index 2. So even for R, yeah. Okay. There is a simple Aragon split. GK is even pro-solvable. For some reason, it has profinite structure, but it's very far from simple. So for that, I think nothing works here, and maybe for such, they're even not MC. Yeah, this was very surprising for me, that the rational points, if you drop splitness, they may be really crazy, far from simple, very far. Okay, so briefly on part 3, but I should say something. So 3 is the bachelor thesis. Of Maciej Frącek. So third year undergraduate student who will defend on Monday. Okay, so I mostly just talk. When we were working on this, I was trying to see what happens for unipotent ones. And for the simplest unipotent, unitriangular 3 times 3, which is Heisenberg group factor. I was pretty sure everything works nicely, so I gave it to him as bachelor thesis project to check some things. He immediately noticed what I asked was false, and then we were looking a bit more. So the problem was we didn't have anything like Borel-Tits, but something exists. So another theorem was useful. Oops. Was his PhD thesis. So he classifies abstract automorphisms of unipotent groups. He says they decompose into one of 6 types. Some unipotent, not all, I think, but I may say. So using this, Maciej shows something like Borel-Tits for Heisenberg. Probably it will work in greater generality. Here actually it cannot be avoided. Characteristic should be different from 2 and 3. And one can see the reasons for Heisenberg should be different than 2. So what he showed, if characteristic of 2 fields is not 2, and we have monomorphism, then basically conclusion is here. The conclusion, okay, it's something weaker, but good enough. Then there is field homomorphism and automorphism of group of rational points, not necessarily algebraic, but it doesn't matter. such that the same. Okay, we have the same decomposition. Just on this level, this is not necessarily algebraic automorphism, but we don't care for the conclusion. It's still elementary. Okay. So actually, he showed more. Characteristic not two yet. So that's the last statement. It should be also true here, I guess. It's even if and only if. For the opposite implication, we use, I think, the theorem of Maltsev that Heisenberg group interprets, defines a field. You take the center, which is this matrices, just non-zero element in top right. You restrict multiplication, it becomes addition, and there is a formula, universal formula, to define multiplication, universal formula in group language, to define on it extra operation, which is multiplication of a field. And that's used for another implication. Okay, in the future, of course, we would like to go to general view like this. And still we didn't have a look. I guess this theorem will be true without this assumption, but by some other methods. There is some type of automorphism which has to be used for that, and it requires dividing by 2. So it's characteristic. Yeah, okay, that's it. Thanks.
Any questions?